To Reyes. This is the last talk of the fifth week, and it's a real pleasure to welcome our next speaker. His name is Felipe Ortega Gama. He's a second-year PhD student in theoretical physics at University of William and Mary. If you're not familiar with William and Mary, it's a university that is very close to Old Dominion, where REYES is being hosted. His research interest is very closely aligned to my research interest. He works in the theory of quantum chromodynamics. In particular, he's interested in using numerical tools. He earned a master's degree from the University of Waterloo in Canada as part of the Perimeter Scholar International Program. This was a couple of years ago. And right before that, Felipe joined us at Jefferson Lab to do a summer internship, working with me in a research project, and we wrote a paper together a year ago, and we're working together continuously. He's a rising star in our field. Before all of this, he got his bachelor's degree in physics from the Tec de Monterrey, Mexico. And in addition to this talk that he's going to be presenting to us today, he's going to be part of the panel of that is going to be hosted in a couple of weeks of students that are coming from Mexico to Jefferson Lab and other international labs. And so he's going to be telling us about his experience in that program. With that, I give the floor to Felipe, who's going to tell us about symmetries and the role that they play in physics. Thank you again, Felipe.
No, thanks to you, Raul. Thank you for that very nice introduction. It is a pleasure to be here, and I'm very glad you invited me to give this talk for the REYES summer program. And as Raul said, I'm going to talk about symmetries and how we use them on physics. So you might be familiar with the concept of symmetries from the point of view of art, for example. It is very common to think of a piece of art to be beautiful if it has a certain kind of symmetry. For example, the background picture that I have here is a piece of art called the Cosmovitral, and it has an inversion symmetry, which means I can flip it from right to left, and the picture would stay pretty much the same. Thanks to this property, our sensors are pleased after looking at this picture. So similarly, in physics, you can have symmetries that can help you not only please you, but it can also help you to understand better your system. So to begin with this talk, I want to go back to the beginning of the 20th century, in particular with a German mathematician called Emmy Noether. Emmy Noether, she was herself a mathematician. She wasn't interested in particular in physics, but she thought that in general, there might be a general abstract framework that she could apply to physics in order to have a broader picture of the interactions and the frameworks that were appearing at the beginning of the 20th century. So as you might know, at the beginning of the 20th century, Einstein came up with his theory of relativity. This theory was an improvement on top of Newtonian's relativity and was able to improve our and have more precise results on the description of planetal orbits and also on the overall cosmological dynamics that up to today we're still measuring more precisely and confirming the theory of Einstein. On the other hand, other physicists like Schrödinger, they were able to come up with a new framework to describe the very small, in particular the atoms and the subatomic particles that make up the atoms. This theory was called quantum mechanics, and it was able to describe the dynamics of electrons and how different elements and compounds can interact with each other and understand why the periodic table is arranged the way it is. But Emmy was more interested on how these frameworks, how can we simplify these frameworks, or how can we exploit these frameworks to understand what they are describing. And furthermore, she was also interested in the constraints that the frameworks pose to the system itself. That means she wanted to know if, in particular, given a specific physical theory, you can tell which players can go and have dynamics in that theory. So in order to make an analogy of how her discovery works, let's think about the ice rink. Let's imagine for a moment that an ice rink is our universe. And then if we go and zoom in a very particular patch of our universe, we will realize it has certain properties. So for example, if I rotate around this particular patch, I would pretty much see the same ice, smooth ice around me. I will be able to rotate around and still see the same surface around me. What's even more, I could move a little bit to the right or to the left, and the system surrounding me would still be the same. This is what we call asymmetry in physics. When you can change or do a physical change to your system without changing the outcome of an experiment. So for example, by rotating around, I would still observe the same patch of smooth ice around me. And this allows us to do certain things in ice rings that we wouldn't be able to do otherwise. So for example, so these are called local symmetries, since we have to zoom in a particular patch of the ice. So in particular, these symmetries allow us to do things like what Tara Lipinski is doing in this video from the Olympics of 1998. Thanks to the rotational symmetry, she's able to rotate around on what we call angular momentum conservation. So in physics, we use certain symbols and equations to describe what is going on. So in particular, we use the letter L to describe angular momentum, and this D means a change. So T means time in this case. And so this equation in particular means that there is no change in angular momentum, or the change in angular momentum is equal to 0. Thanks to the rotational symmetry of the ice rink, she's able to conserve the angular momentum up to the end of the video, where she's able to dissipate that angular momentum by stopping. How does she do that? Well, she has to pierce the ice with her skates. Thanks to that, she's breaking the symmetry of the ice. By piercing the ice, she's creating a particular that doesn't look the same from any direction anymore. And by breaking the symmetry, she's able to dissipate this angular momentum. So in physics, there's the Noether's theorem, thanks to Emmy Noether, that allow us to relate symmetries to transformations. So we have a rotational symmetry. There is a transformation that rotates us around, and that equates into a conservation law. So for every symmetry, you would have a conservation quantity that is going to be conserved. So for example, rotations are normally described in terms of angles. How much you rotate around a certain axis gives you a transformation. And what's even more interesting is that different transformations can be added together. So I can take two rotations with different angles and add that rotation together into a single one. And this is a mathematical framework. There is a mathematical framework that studies these particular types of equations, if you want, that's called group theory. So using group theory, you can demonstrate something that might sound very logical, but that it's of course true, and you can demonstrate that mathematically, that different things, different stuff will transform in different ways. So for example, a circle under a rotation and a triangle under a rotation will transform in a completely different way. In order for the circle to have a symmetry, you can rotate it around whichever angle you want. But for the triangle, you can only rotate it in thirds of a turn. These different things, different properties that objects have, allow us to classify them in different ways. This is what we call normally particles. So in this case, I can assign an angular momentum of 0 to the circle, since it has a trivial rotation property, whereas the triangle, which has a specific rotational property, I will assign an angular momentum of 3. And since in a system where you have a rotational symmetry, the angular momentum is conserved, the triangle is going to stay as a triangle forever, and the circle is going to stay as a circle forever. This can simplify your physical calculation enormously, since you will be able to label different things in a specific way and know that these things would stay the same throughout all the calculation. So in our universe in particular, locally, we have Poincaré symmetry. Our universe is Poincaré symmetric. This means that there is a rotational symmetry. You can rotate around in any of the 3 spatial dimensions, and the universe would still look the same. And there's also a displacement symmetry. You can move around in space and even in time, and the universe would stay the same. These symmetries allow us to use quantum mechanics and group theory, the 2 frameworks that I described before, a physical framework and a mathematical framework, to label all the players in our universe with these 2 labels, L for angular momentum and M for the mass. So all the particles in our universe, according to this mathematical framework, can be labeled with these L and M. So up to now, we know there are these particles in our universe. There are the quarks, the leptons, and the bosons. Each of them is different from each other, and we can tell them apart because they have different values for L, different values for their mass. The quarks and the gluon are the particles that make up the strong force, which is the particles that interact inside of the atomic nuclei. These are the particles, as Raul mentioned, that I'm more interested in my field of study. But you might wonder, how come we ended up knowing that these are the particles indeed that build up all of the atoms in our universe? So in order to explain that, I have to go back to the 1930s. In 1930s, there was a scientist called Harold Urey that worked in the National Bureau of Standards in Washington, D.C., and was able to discover a very a very similar molecule to water that behaved chemically pretty much the same, but that it was heavier. It had a slightly different density. So from the different densities, you can make heavy ice and normal ice and put it in a cup of water. So in this picture, for example, you can see heavy ice that sinks into the bottom of the cup, whereas normal ice, as you might be familiar with, will just rise to the top. He found that this heavy water had a slightly different density, and that this change in density could be explained if, so as you might know, the water is a molecule with 2 hydrogen atoms and a single oxygen atom. And he found out that the difference in densities could be explained if the hydrogen atoms in the water molecule were replaced by a different molecule that he called deuterium. So this molecule deuterium, this element will have to have the same chemical properties, but twice the mass of hydrogen. So later in 1932, thanks to different experiments made by James Chadwick at the Cavendish Laboratory in Cambridge in the UK, he was able to split up the deuterium atom. He found out that it was also made of 1 electron surrounding the nuclei, but that the nuclei itself had 2 different particles. One of them exactly the same as the nuclei from the hydrogen atom, and a new one that hasn't seen before, and that's what he called the neutron. So the neutron and the proton, they have a very similar mass. Chadwick was able to measure very precisely the mass of the neutron. He found out that it was a few percent away from that of the proton. So here I am writing down the masses of the proton and the neutron. And as you can tell, in kilograms, we are using a scientific notation to mean that there are 27 zeros to the left that we are not writing down. So for convenience, we just write them as 10 to the minus 27. So because atoms are very small, they don't weigh a lot. However, physicists, because of the inconvenience of these of kilograms, they use a different unit to measure masses. One of them is called megaelectronvolts, MeV for short. So using this unit, the masses of the proton and the neutron would be translated into 938 and 940. As you can tell, these masses are very similar. So somebody came up with the idea that maybe they're actually just the same particle. There is just a symmetry there, but it's just slightly broken. And this is a small breaking of the symmetry is what gives rise to this small mass difference. So that was Heisenberg. Well, not this Heisenberg, but Werner Heisenberg. The German physicist in the 1930s thought about the idea of an extra symmetry, a symmetry that would relate protons and neutrons. So similar to the rotational symmetry that exchanges left and the front. He thought about an internal symmetry that would exchange neutrons for protons. And because the symmetry was slightly broken, you would have slightly different masses. But he thought, nonetheless, this symmetry, if it's just slightly broken, it can still work. And he called this symmetry Isospin symmetry. Later in the 1940s, there was another discovery of a new particle. There were several scientists that used photographic plates to explore what is called cosmic rays. Cosmic rays are basically particles that are coming from outer space that are generated by stars, by quasars, and other cosmological objects that when they come into contact with the atmosphere on Earth, they collide with the particles in the atmosphere and they generate showers. And using photographic plates, we can detect these showers and study the particles in the photographic plates. So Cesar Lattes was an experimental physicist from Brazil that developed a new kind of photographic plate. Thanks to this, he was able to study the pions more precisely and to get the masses and the electrical charges. He found out that the masses of these three different particles were very close together. And therefore, he concluded that although these particles had different electric charges, they must be part of the same isospin triplet. So an isospin triplet means that they are the same particle on their isospin symmetry, but they are just three different kinds of them. So using this isospin, we were able to classify the particles that we had discovered so far. So there were the pions that were in an isospin triplet, 3 of them. There was the proton and the neutron that are in an isospin doublet. There are 2 of those. And there is the deuterium, which is in an isospin singlet because it's by itself. So to each of these particles, we assign a label. So similar to how we assigned labels at the beginning with the L and the M, there is also the label I for the isospin symmetry. So each of these particles will have a particular label. Using these labels, we can actually know what is going to happen when we collide these particles together. So for example, we know that when we collide a proton and a proton, because they have each an isospin of 1/2, they would have to produce a deuterium and a pi plus, since the sum of these two has to be isospin 1. Similarly, when you collide a proton and a neutron, because the isospin cancels, one of them being 1/2 and the other one being minus 1/2, the total isospin of the final system has to be 0. So the deuterium and the pi 0 have isospin of 0. And what is even more interesting is that because the systems are related by an isospin transformation, if you measure the rate of interaction in one system, you can predict the rate of interaction in the other system. And this was the key result that led us to confirm that isospin was actually an almost precise symmetry of nature. So everything was fine until then. But then by the 1960s, using these photographic plates techniques, they were able to find dozens of new particles. And these particles had the issue that they were not being classified easily using this isospin framework. So you had you had what people call the particle zoo, because each of these particles would have completely different masses. Their interactions wouldn't obey simple isospin rules, like the interactions between the proton and the neutron. And people were not really sure how to describe them all. So that was a big problem until the 1960s, when Murray Hellman came. He was an American physicist who proposed a new classification system. He came up with a new quantum number that we call strangeness, and we labeled with an S. So here you can see the old pions that I mentioned before, the pi minus, pi naught, and pi plus, and also the neutron and the proton. So because those particles were fine before this classification system, he assigned them a strangeness number of 0. And then he assigned different strangeness numbers to other particles depending on how close together they were on their masses. So for example, there were particles that had masses around 1230 MeV, and they had different electrical charges, but he classified them as the same delta particle since they had similar masses. It's the same with the sigma particles and the cascade particles. But since their masses increased, he assigned different strangeness values to them. And using the group theory mathematical framework that I described before, he was able to show up that there must be an extra particle called, so he showed up that this difference between these masses had to continue the same. So he found the pattern, he used the mathematical framework of the group theory, and proposed the idea that there must be an extra particle called the omega baryon with a strangeness of -3 and 1600 MeV of mass. And we were able to confirm that experimentally some years afterwards. And his discovery was very close, his proposal was very close of the actual discovery. And the difference is just because this symmetry is just an approximate symmetry. If all the particles had the same mass, this would be an exact symmetry of nature, but this particular symmetry is slightly broken. He was able to propose that all these patterns were given rise because there were 3 quarks inside of these particles. So he was able to show that if you come up with different combinations of these quarks, you were able to explain all the different particles that had been discovered up to this moment and explain their mass differences. And he proposed that these strangeness numbers were basically telling you how many strange quarks there were inside of each of them. And the charge of the particles were telling you how many or what was the combination of up and down quarks inside of them. So this was a success story for symmetry when we were able to use it properly to make a very good prediction about a new particle that was later confirmed and explain a lot of the patterns in the particles that had been discovered during the 1960s. However, symmetries are not always the best to use in physics, since they have to rely on our universe actually having that symmetry. There's a symmetry called parity. In physics, parity means that you will take a system, you will look at it on a mirror, and you will replace the system by its mirror image. So for example, if you have an arrow pointing to the right, and then something rotating around that arrow, and you look at that same system on a mirror, the arrow will be pointing in the opposite direction. But in a mirror, the rotation will not change direction. So in one of the systems, your arrow is going to be pointing. If you look from the point of the arrow, the rotation is going to look clockwise, but in the other system, is going to look counterclockwise. And at the beginning of the 20th century, most of the physicists thought that this was indeed a good symmetry of nature, that our universe was parity symmetric, and therefore all of our interactions had to respect the symmetry, and that we could assign a quantum number related to the symmetry to all of our particles. However, as you might know, for example, my face is not parity symmetric. If I put a mirror image of my face next to each other, you can clearly tell it's not the same as my actual face. And in particular, physicists were able to demonstrate that when you have a kaon particle, a K particle, when it decays, it normally, if you prepare your system in a certain way, it will normally decay into 2 pions. However, if you replace the system by its mirror image and you prepare it differently, you would find out that this same K particle will instead decay to 3 pions. So originally, what was happening was that the physicists were not able to tell that these were indeed the same particle, because they insisted there had to be a parity symmetry. They thought that these had to be 2 different particles with different parity quantum numbers. However, because all the other labels, the mass, the spin, the angular momentum, the lifetime of this particle matched exactly, they had to realize that parity couldn't be a good symmetry of nature. And later, other experiments confirmed that in other systems, parity was not indeed conserved. And therefore, that was the end for parity as a symmetry of our universe. So basically, the rest is history. After dropping parity, we were eventually led to the proposal of other quarks. Since you needed a specific framework for parity to be consistent with the current equations of physics, you needed to propose an extra quark, the charm quark, to exist. And it was later confirmed experimentally. Similarly, there's another symmetry called charge conjugation. And as before, physicists thought that maybe charge conjugation was still a good symmetry of nature. They realized experimentally later that it wasn't. But for the system to still be consistent, they had to propose another 2 quarks. Later, they were finally measured experimentally, and even when symmetries are broken, they can still lead us to have a good prediction of what is there in our universe. Other particles, like the CW and Higgs particle, are the result of what's called a broken symmetry. In particular, the photon, which carries the electromagnetic force, the electricity that we see every day in our houses, in principle, it has a symmetry between all these particles, except that this symmetry is badly broken, giving very high masses to these other particles, whereas the photon is a massless one. However, if we understand, because we understand this breaking pattern so precisely, we're able to predict the different masses in terms of one another and the interactions of all these particles given a few data points. So this is all to say that symmetry can be used as a very powerful tool. Even when a system is not exactly symmetric, or even badly, the symmetry is badly broken, you can still use this as a tool to predict things, to know what are the players in your dynamical theory, and to simplify your calculations to be able to understand the physics more properly. So as a final remark, I was asked to propose some further reading for you. I would recommend 3 books in particular, depending on what you're interested in. So one of them is called The God Particle by Leon Lederman. This book talks about all the discoveries of the 20th century, or most of the particle discoveries of the 20th century, from the point of view of a particle physicist, of somebody who actually won a Nobel Prize by his research and his discoveries on particle physics. Another book, which was in a sense the inspiration for this talk, is A Brief History of Time by Stephen Hawking. This book is non-technical. It talks more about the ideas behind physics and the particles and the symmetries that are behind our physical theories, from quantum mechanics to the theory of relativity. And finally, a book that I really like that covers the mathematics of group theory very precisely is Lie Algebras in Particle Physics by Howard Georgi. This book is rather technical, but it is the tool that physicists use, the mathematics that they use in order to exploit the symmetries and understand the system. So given that, I'm thankful for your time and your attention, and I open the floor for questions.
All right. Thank you so much, Felipe, for a really nice introduction to symmetries. Let's give time for people to ask questions if they have any. There's a little bit of a time delay, so we'll have to wait to see if we'll give people a couple minutes to see if they have any questions. Maybe in this time, maybe you can tell us a little bit about how perhaps you've used, or if you've used symmetries in your research.
Yeah. So in my research, for example, there is a particular way that we use symmetries that I find very interesting, which is because we use numerical simulations to understand quarks and gluons, we have to place them into a computer. And when we place them into a computer, we cannot place them in a universe like ours. We have to make some approximations. One of them is that they have to be placed in a finite volume, in a box. We normally use a box to place them. And since the box breaks this rotational symmetry that I was speaking about before, the angular momentum label is no longer a good label to identify the different quarks and the different excitations and the different particles that show up in our numerical simulations. So instead, we have to use some group theory to come up with the proper labels to use for our lattice, for our simulations, to label each of the particles that we will extract, and then to relate them to whichever particle you would see in the actual physical universe.
All right, thanks for that.
This is my favorite application of symmetries in my research.
That's good. That's a good one. So we have a question and a comment from Sergio Gam from Mexico. Sergio doesn't say the city. Saying, great talk, and asks if you can explain the idea of supersymmetry.
Well, yeah. So supersymmetry is another proposal of a new symmetry that is similar to isospin. It's not really a symmetry where you rotate around, but it's a symmetry where you exchange certain characteristics in between particles. So in supersymmetry, you would exchange, for example, quarks and bosons. And this has been a very exciting proposal since it is part of what we call string theory, which is a theory for quantum gravity. However, experimentally it hasn't been found. Even if it's badly broken, different experiments have been looking for it for some time, some decades already, a pair of decades, I would say, and they haven't found any evidence for this as a symmetry. So up to now, it falls into the category of a bad symmetry, since there is not yet any experimental evidence that it is indeed a good symmetry for our universe.
And in particular, what would be evidence?
So if we found a set of particles where the supersymmetric partners of the particles that we already know, we would be able to tell that the supersymmetry was a good symmetry. So similar to how isospin, if you had the proton, for isospin to be a good symmetry, you had to have the neutron. And if you had the pi plus, you had to have the pi minus. And all of them had to have similar masses. So it would be the same in our universe. If it was supersymmetric, you would have the up quark and the supersymmetric partner of the up, and the photon and the supersymmetric partner of the photon. But even though we have been looking for these particles for quite some time, even if the symmetry is badly broken, we haven't been able to find these super partners.
Oh, unfortunately, I have some dogs barking here. So if you hear some dogs barking, I'm sorry about that. But that was a great response. Okay, so we have a question. We have a few questions, and one of them, some of them will take me a little bit of time to translate. This one I think is pretty easy, or at least for me to read it. Jaime Vasquez Madera from Ponce, Puerto Rico says, "Good afternoon. How do we truly know that the standard model is officially complete? Are there still uncertainty when considering symmetries that leave empty spaces in the model, which can imply that there's still more particles we have not put into perspective?"
That is a great question. So I don't have here the full standard model, so I have to go back to the beginning of the presentation where I have it. And the answer to that is that there is one particle that doesn't behave as we expect exactly, and that's called the neutrino. Normally, the standard model, as it was originally formulated, it expected the neutrino to be massless. But recently, there have been lots of experiments showing that the neutrino is not massless or cannot be massless because of certain properties that it has. So this label M cannot be zero, basically. So these are the neutrinos here, the neutrino electron, the neutrino muon, and the neutrino tau. So if we are able to understand better the neutrinos, which we could be thinking about new particles that can, for example, connect the standard model with dark matter. So dark matter is another property of our universe that astrophysicists were able to see, and their models say there has to be another type of matter that is not part of the standard model, and they call that dark matter. And some proposals, for example, think that the neutrinos have partners that are very massive. So normally neutrinos are thought of left-handed particles because of certain properties they have on their parity, indeed. So because they behave in a specific way on their parity, we call them left-handed. And we think that there could be right-handed partners of these neutrinos, which will be very massive, and they could be an explanation, perhaps, of dark matter. So that's one of the main mysteries of extra particles that could be indeed completing the standard model and solving perhaps other problems in it.
Great. And also for those of you that are interested in possibilities of extensions to the standard model, I would point to two previous talks, one by Saul Ramos, which is in Spanish, but he's about to give it again in English later in early August, where he talks about string theory. And so if you don't understand the Spanish version, don't worry, he's going to give another one in English. The other one that I would point you to is by Max Hansen, where he talked about the history and the future of CERN. And so he talked about some motivations for future experiments in that context. Okay, so here's a question, which I don't know the answer to, and maybe you do, which is by Deja Alexander, Chesapeake, Virginia, saying, so do you know if heavy ice is common in America or other countries?
So,
ahead.
yeah, it's very uncommon. Harold Urey had a lot of trouble synthesizing heavy water because it is actually on normal water, but it's in a very low density. So because of the different properties it has, you can evaporate some of the water and you would leave behind some of the heavy water and do that process again and again, and then synthesize a big amount of heavy water. So in general, most of the water has more or less the same proportion of heavy water around the world. And nowadays it is used mainly for nuclear reactors, for example. It happens to be a useful tool for nuclear reactors. And it has to be produced in an industrial way in order to, to be sold and used. So it's not something you will find, on a lake that happens to be heavy water, but it's mostly diluted in normal water.
All right, great. So we have a couple more questions. One from Luis Angel Vergara Ortiz from Hidalgo, Mexico, saying, great presentation. So what if we said that there's no neutral charge or condition, and there is just a combination of positive and negative states to give place to a third state? How would symmetry describe this?
So I'm guessing he's talking about the neutron. Maybe there's not a neutral particle, but there's actually just a combination of electrons and protons. And that's what actually the neutron is, and it's not actually an extra particle.
Perhaps.
So if that's the question, the answer is that we can, using quantum mechanics and our physical frameworks, we can know the precise energies that a bound state between proton and electron can have. So you can study them, and you can also know the spatial extent they would have. So since electromagnetism is kind of a weak force compared to the strong force inside of the nuclei, you should be able to tell that the proton with an electron surrounding it has to be something completely different from a neutron, from the point of view of the spatial extent, and also from the point of view of the masses and the energies these two systems will have. So that was my interpretation of that question.
Yeah, why don't we let Luis Angel, why don't you send us a message and let us know if this answers your question, or perhaps you want to rephrase your question a little different. We have time, so please go ahead. Okay, so we have a question from Christian Gott from Hampton, Virginia, asking, what does the graviton do? Or what is the role, what is the graviton, perhaps?
Yeah, that is also a good question. I didn't talk too much about the graviton, and it's actually indeed in this picture because I'm not exactly sure why they put it in this picture, but it's not precisely in the standard model. The graviton would be the theoretical particle. It hasn't been discovered, it hasn't been observed. That would be the excitation of quantum gravity. So similar to how the photon is the excitation of electromagnetism. So light is made out of photons. Then gravity or gravitational interactions will be made out of gravitons. So that's the proposal, that's the idea behind the graviton. However, because gravity is even weaker than electricity and electromagnetism, we haven't been able to measure this particle. And also, the other problem that we have with the graviton is that if we try to put gravity in the same theoretical framework that we have put the rest of the particles, we are not able to make the theory fully predictable. So we can, write an equation, describe gravitons, but this theory would break down at some point since it wouldn't be able to predict what will happen with the system at all the possible conditions. So the graviton, it is still there since it will be the natural extension of gravity to the standard model. However, up to now, there hasn't been a consistent physical theory that includes the graviton with the standard model, and also there hasn't been any experimental observation of a graviton yet.
Maybe do you want to mention what characteristics that would it have to have that would make it different? You know, why couldn't, what would
So
be?
the graviton, yeah. So the graviton, for example, will have to interact with all the particles attractively. So for example, electricity and magnetism, that depends on the positive or negative charges. So if you have positive and positive, they would be attractive, but if, I mean, they will be repulsive, but if you had positive and negative, then they would be attractive. The graviton, because of its characteristics, it has to be attractive between all particles. So that's one difference. The other difference is that it has to have some kind of universality in the sense that it has to be able to interact with all of them. Different from, for example, the gluon that only interacts with the quarks. The gluon, for example, it doesn't interact with the neutrinos or the electrons. It is selective in the sense that it can only see quarks when it moves around. On the other hand, the graviton wouldn't have that freedom. It would have to be able to interact with all of them in an equal footing, in a sense, and it has to be also always an attractive force, different from the photon or the gluon that they can be sometimes attractive and sometimes repulsive.
But did you mention its angular momentum?
So yeah, the difference also is that the label of the graviton would be an L with number 2, whereas the gluon, the photon, and the CW bosons, they have a label of L equals to 1. And the quarks and the leptons, they have a label of a half spin or half angular momentum.
So
different label also.
Right. Okay, so Luis Angel got back to us and said, yes, it kind of answers. But, and then he goes on, I think he meant to apply the question not just specifically to this one case, but more broadly. I think we kind of answer at least for one case, so perhaps we can call that a success.
If it doesn't work in one case, then it won't be able to work in all the cases.
Right. So Javier Vasquez Madera from Ponce, Puerto Rico said, you mentioned deuterium earlier in the presentation. Can you also give a brief explanation of what tritium is, its properties, and why is it unstable? And is it true that the moon has sufficient amount of tritium for us to harvest it?
So for the last part, I might not be able to answer that question since I'm not a moon expert. However, similar to hydrogen and deuterium, tritium would, you can imagine, you can have an extra particle here called tritium. It would have the same chemical properties. That means it would also have one electron surrounding it. But the difference would be that instead only proton and neutron, it will have a proton and 2 neutrons. Because this system has, well, it is not exactly understood fully in the sense that we have a good equation that describes this, but we are not able to fully solve this equation exactly yet. This is part of, in a sense, my research. These specific binding between proton, neutron, and an extra third neutron is not completely stable. It's a metastable state. So after some time, if you're somehow able to mix together, for example, if you collide a hydrogen atom with a deuterium nuclei, you can have, by chance, that the proton decay transforms into a neutron, expelling an electron and a neutrino, and you will be able to have a bound state between two neutrons and 1 proton. However, this is not so it also has to do with the fact that neutrons are heavier than protons. So after some time, the neutron wants to go down in energy. So it would release some energy, it will become a proton, and they will split from the nuclei, forming again a hydrogen and a deuterium. So in a sense, it also has to do with the fact that neutrons are slightly heavier than protons. So that configuration is not as stable as just a proton or a proton and a neutron. For the moon, I don't know. I don't think so, because the tritium has relatively low time life, so it would decay before.
Yeah,
I know we can produce it here on Earth, so.
Yeah, I was just looking this up. The lifetime, the half-life is, well, it's 12 years, but no, I don't think it.
Yeah, so probably whatever is there on the moon has been for like at least 1 million years, if I'm trying to guess correctly, more or less what's the age of the moon. So probably that's something that decays in 12 years would have been long gone by now.
Yeah, and I think it decays primarily to helium-3 through a beta decay. So
in that case, goes to a proton, and neutron. Okay.
And that forms a bound state. Yeah. So yeah, if you're interested in that kind of decay, I described it a little bit. I described the neutron decay in our Python for Physics course in the 3rd week. So if you're interested, look back at that. Okay, I think that about covers the questions. Let me check one more time. Yeah, I think that covers everything. So thanks again, Felipe. Let me just let everybody know. So this wraps up this week for Reyes. We're gonna come back next week. On Monday, we should be releasing towards the end of today a video giving a summary of what's up in the week. So I would point you to that. Go check that out. But also the calendar is up on the website as always, where you can find the recording for all the sessions that we covered before, and the recording of this video should be up there soon. So if you want to watch it again, you're welcome to. I want to recommend to all of you to join us on Monday, where my friend Emi Trawartha will be talking about using artificial intelligence to analyzing all the literature that is coming out about COVID. This is a new idea. It's quite interesting. Her background is in physics, and she's applying this in a whole different new field. So I think it's going to be quite fascinating. So I would highly recommend for everybody to join us for that. And so with that, thank you again, Felipe, for taking your time and giving us such a nice presentation.
Thanks again, Raul, for the invitation.
All right. So take care, everybody.